How do we measure energy? First of all, not temperature. Energy is not the same thing as temperature. We can measure the transfer of energy by measuring something, whether something goes up or down in temperature, but it's not actually, a temperature is not a direct measurement of energy. Does anybody know some energy units where we measure energy in? Calories is one. Another one is the joule, capital J. You know any other ones? The what? SI is a category of units. So the SI unit for energy is the kilojoule, I think. Look that up. I think that's right.
Is joule the same as glucose?
No, glucose is a molecule. No. Some other ones, those are the common, these are the important ones, those are the most common ones, and we'll talk about them a little bit more in a second. Some other lesser known ones, the BTU, the British thermal unit, sometimes is an important measure of energy when you're talking about like fuel or heating, like your furnace or your air conditioner is probably rated in BTUs of energy. Does anybody know how energy is calculated or measured at your house? Like when you read the electrical meter? What do they read? What is that unit? You know? That is the kilowatt hour. So if you look at your energy, you look at your electric bill, that's how they measure the amount of electricity that you're using. Now, different measurements are used, or different units are used for different situations, just depending. Like that happens to be one that we use for houses because the units end up being kind of nice. Like you use however many 50 kilowatt hours a month. That's like a nice unit area. If we measured that in joules, it would be this giant number, and it would be harder to manage. So. The ones we're going to focus on for this class are the calorie and the joule. And the calorie is defined as the amount of energy it takes to raise 1 gram of water 1 degree C. So if you have 1 gram, remember 1 gram of water is a milliliter. This tiny block. So if you have this much water, and it's right now at whatever the temperature is here, 23 degrees or something, and you want to raise it up to 24 degrees, it takes exactly 1 calorie of energy to do that. And that's scalable. So that means if you have a liter, 1,000 milliliters, and you want to raise that 1,000 milliliter of water by 1 degree, how much energy does it take? 1,000 calories. Each one takes 1 calorie to raise 1 degree C. If you wanted to raise it 5 degrees, this whole thing 5 degrees, it would take 5,000 calories. So that scales like that. And that's where we get that energy. So this is a really nice unit for measuring things in the lab because we can easily measure our water changing temperature, and then we can figure out how many calories of energy it took to change the temperature of that water. And that's one thing that you're going to do in lab today. The joule also has a definition, but we can think of it in terms of calories. The conversion is that 1 joule is 4.184 calories. So a joule is smaller than a calorie. There's a little over 4 joules in a calorie. And just like any of these other things, you don't need to know that number. I would give you that number. And so we can convert from calories to joules depending on what we need. Now let's talk about food. You probably recognize that term calories from food, right? Is that the same unit?
1 calorie for food is kcal. So
Yeah, and this is a confusing thing. So if you look carefully at your food labels, here I have one here. Did else have some food out that has a label? I don't think so. Okay, we'll look at mine. Anybody know how many calories are in a bottle of Coke?
A lot.
A lot, yeah. Are you judging my food choices? Is that? There it is, okay. Okay. You see it? How many calories are in there? Oh, 140, right? Is there anything that indicates that this calorie is different from the one that we just talked about? There actually is. It's a very slight difference. It is that it is a calorie with a capital C. So a calorie with a capital C is not the same as a calorie with a little c. In fact, it is 1,000 times different, 1,000 times bigger. And that is why it is really more clear to talk about those calories as a kilocalorie. And pretty much everywhere else except the US, that's how you would see it. That the nutritional information on a label would be given in kilocalories so that it's clear that we're talking about 1,000 of the regular calories. On our labels, the only thing that shows us that is that it's a capital C. And it's especially dumb because C is one of those letters that the big one and the little one look the same. So if you just drew it a little too big or too small, you're suddenly off by 1,000. Seems like could have come up with a better way to do that. But you should know that that's the case because part of what we're doing in lab today is calculating food calories based on what's inside them. All right, so let's practice that. We can estimate the amount of calories in food and actually get pretty much be right about it based on the sources of calories in food. So there are 3 broad categories of calories in food. What do you think they are? So give me one of them.
Carbohydrates.
Carbohydrates is one. Fats. And the third one is protein. Yeah. Those are called the macronutrients. And those are pretty much all the sources of energy, the source of calories in your food. So you've got carbohydrates, fats, and proteins. Okay, how are those sources of energy? What does that mean? What does it mean for that to be a source of energy for your body? How is the energy stored in those types of things?
There's 4 kcals per gram in carbs, in proteins, and 9.
Oh, yeah. So that's the quantities, and we'll talk about those in a minute. But what causes that? I guess I might as well write those down. So carbohydrates have 4 kilocalories of energy in every gram. Fats have 9. And proteins have 4 as well. But why? What is it? What are these things, carbohydrates, fats, and proteins, and why do they contain energy? Ideas? It's the bonds, the chemistry involved. These are molecules. Carbohydrates are molecules like starch, like glucose, like sucrose, those kinds of things. Fats are molecules, and proteins are very, very large molecules. And they're made mostly of carbon, hydrogen, oxygen, and nitrogen. And the bonds between those atoms store energy, and our body can break those things down and release that energy from those bonds. So what does this tell us about the relative energies here? What does it mean that fats have more kilocalories per gram than proteins or carbohydrates on average?
That make the bonds easier to break?
Not necessarily. It kind of depends on what the chemistry is doing in your body. But what it does tell, it says something about our density. So remember we talked about density in terms of grams per milliliter? Well, there's another kind of density also, what we would call energy density. How much energy is in a certain amount of stuff? So what is the more dense energy source? And which of those 3 is energy stored most densely? The fats, right? Because for the same amount of stuff, you can get more energy out of it. So fats are a more efficient, or you might say, or a better way of storing energy. They contain more energy. So what you can do, and this is what we'll do in lab, is you can look at how many grams of carbohydrates are in your food, how many grams of fat, and how many grams of protein. Multiply those by these given factors and figure out the total number of calories. Now, does this seem like a particularly precise way of doing it? I mean, not really, because there's different kinds of carbohydrates, there's different kinds of fats, there's different kinds of proteins. Those are all going to vary a little bit. So that's why we don't use a lot of significant figures. You'll notice I said 4, 9, and 4. That's what your book says too. I didn't say 4.00, 9.00. And that's because there is a variability there. So it's going to be between like 3 and 5. And when you look at the package for your food, 140 calories, that's probably really just 2 significant figures. So that's really saying that the calories are between 130 and 150. So we're basically making the assumption there that we don't need to be that precise in these measurements. These aren't measurements that need to be super, super precise, and that's why we use the numbers that we use. So we'll practice in lab doing calculations with those, and there's some of that in the homework as well. Let's look at something called specific heat. Specific heat, or heat capacity, we're going to define as the amount of energy it takes to raise 1 gram of a substance 1 degree C, or 1 Kelvin. So that definition looks a lot like something we just wrote, right? We go back up, remind ourselves. We just wrote that a calorie is the amount of energy it takes to raise 1 gram of water at 1 degree C. So what's the specific heat of water? 1 calorie, yeah. There's kind of a weird unit here. The units for heat capacity or specific heat is calories or energy per gram degree C. And that's kind of the math way of writing what we just wrote in a sentence, the amount of energy it takes to raise 1 gram of substance 1 degree C. So water is 1, just like density or whatever else, we've defined it that way. We can also say that the specific heat of water is 4.18 joules per gram degree C. Same thing, but now we're in joules instead of calories. I don't know why I wrote the fraction sideways either, but it's the same. All right, so if that's the specific heat of water, that's how much energy it takes to raise a gram of water 1 degree C, to heat up water. Let's compare that to, let's say, metal, like aluminum. Do you think aluminum has a higher or a lower specific heat than water? What does that mean? Yeah.
Higher.
Why higher?
Because if you're like boiling water in a pot, the pot doesn't melt, whereas the water will start to boil. So. Okay,
well that tells us about the relative melting point and boiling point, and that's true, right? Aluminum's melting point is, I want to say 500-ish C. Yeah. But what about specific heat, though?
Is it because aluminum is more dense? So.
Aluminum is more dense. So does that affect the specific heat? Let's think about it this way, because I think this is a problem in the book, too. Imagine you are outside, like on this beautiful weekend at a pool. Was anybody at a pool? Anybody get to go to a pool? Okay, no, me either. But imagine you were at your pool, at a pool, some kind of fancy pool. And it's a hot day, and there's a piece of metal, like a piece of aluminum out in the sun. And the pool is also in the sun. What do you think gets hot faster, the metal or the water? The metal. Has anybody experienced this? Like metal gets hot really fast. So what does that tell you about its specific heat? It's much lower, that's right, much lower than water. Because it takes, for the same amount of energy, that metal is going to heat way up, and the water is only going to heat up a little bit. You put a bowl of water out in the sun, it's not going to like get that hot for a while, right? But if you put, what? Unless you're in Texas. But still, compared to like what would happen to metal in Texas, it still wouldn't get quite as hot. So that metal is much lower specific heat. So let me show you a table of that in the book here. Maybe. Oh, so there are some specific heats of some different substances. You can compare it to water. So we've got water down here at 1 calorie per gram degree C. And you can see like pretty much everything else has a lower specific heat than water. And that's another reason that water is special and why it's so important to life and all of that. You've got oceans and lakes, and that really helps control temperature, because even land and rock and other stuff like that is not going to have nearly as high a specific heat. So it's not going to be able to store energy the way that water can. And there's our aluminum right there. So only 1/5 of the specific heat of water, which means that for every degree water, or for every calorie, if water goes up 10 degrees, aluminum is going to go up right? 5 times that. Okay. Or it's going to take, another way of saying that, it's going to take a fifth of the amount of energy to raise the aluminum. And then things like copper and gold have even lower, and silver have even lower specific heats. That means that they can heat up really, really quickly. Have you ever cooked with pans? Probably. I don't know. Sometimes, like the fancy pans have that layer of copper. I don't know if anybody's ever seen that. On the bottom of the pan, there's like the copper layer. No?
They don't work.
They don't work?
I don't think there's any difference.
Yeah, there may not be. The idea of them is that it's supposed to distribute the heat more evenly because the copper heats up so much faster. Whereas the iron or the steel, which is mostly iron, is going to have these kind of hot spots instead. That's not, I should say, that's not just about specific heat. That's also about something called thermal conductivity, which is how well does the heat, how well is heat conducted across the material. But they're often similar, they're often related. You can see there's not a whole lot that has specific heats higher than water. We can think about stuff that insulates really well, but often that's more of an issue of thermal conductivity. Stuff like air doesn't heat up that much, but also there's not as much mass of air usually in the same place. So that's part of it. All right, so that's the idea, that's this idea of specific heat. One thing we can look at then, thinking of these things together, is what does it look like when we heat water from ice all the way up to boiling? We can look at a graph like this, which is called a heating curve, and answer some questions about it. So let's see. Big. All right, so here is a graph that shows temperature on the y-axis and heat on the x-axis. Remember that heat is not the same thing as temperature. So as we're adding heat, this graph shows what is happening to the temperature. If the line is going up, that means the temperature is going up. If the line is parallel horizontal, that means that the temperature is not changing. So we see here we start down at minus 40 degrees C with ice. And as we add heat to that minus 40 degree ice, it warms up. Makes sense, right? You add heat to the ice, it starts warming up. But then right when you get to 0, you have to add a bunch of heat, but the ice doesn't actually get any hotter. Why not? It says, yeah, because it's melting, just like it says here. You need that heat to melt the ice. That heat is going into the ice to melt it, and it's not changing temperature. So when ice goes from ice to water, it actually doesn't change temperature. It just changes its state, but it requires a lot of energy to do that. The amount of energy, which you don't have to know this number, it's 80 calories per gram. So it takes 80 calories to melt a gram of ice without changing its temperature. Okay, so then we've got liquid water at 0, and we start heating it up. Heat it up, heat it up, heat it up. It just keeps getting warmer and warmer as we add heat until we get to 100. What happens at 100? It starts boiling, but we need to add enough heat to actually get it to boil, because we need to be able to tear those water molecules away from each other. We don't break the molecules themselves, they're still H2O. We're just separating them from each other. And that separation takes a whole lot of energy. 540 calories per gram. That's little c calories. So let's think about our gram of water again. Our 20 milligram of water. If we heat this up from 0 to 100 degrees, how many calories does that take? To get 1 gram of water to go from 0 to 100. How many calories? 100, because each calorie takes it 1 degree. So if we want to take this up 100 degrees, it takes 100 calories. But then it takes more than 5 times that to boil it, that same amount of water. Without changing the temperature, it takes more than 5 times to boil it. And so that's a lot of energy. So it takes way more energy to change the state than to actually change the temperature. And that's something that we don't always think about, or it doesn't seem intuitive to us because we think like, oh, it's getting hotter, that takes more energy. But actually it's changing the state without changing the temperature that takes the most energy. And then once we're a gas, we can heat it up even further. Okay. So one way you may see this is, speaking of pans and stuff, has anybody ever boiled water on a stove? Hopefully. If not, try it sometime. It's exciting. You should eat something occasionally that requires like heating. So anyway, what happens when you turn the water on? How long does it take before that water gets reasonably hot? What would you say? I mean, it depends on the size of the pan and everything. What would you say happens faster? It gets hot enough that you don't want to touch it, or it boils? Yeah, it gets hot enough that you can't touch it pretty quickly. Try it, time it tonight when you get home. Put a pot of water on the stove, turn it up, and see how hot it gets, or see how long it takes before it's kind of steaming and you don't want to put your hand in it. Don't like actually stick your finger in it because you'll get burned. But it doesn't take long for it to get hot enough that you don't want to mess with it. But then it might still take another 10 or 15 minutes to start boiling. And that's because it takes a whole lot more energy to actually get it to start boiling, to get it to break those interactions, than to just get it hot. And that's what we see here. Okay, so let's talk about these processes in terms of the language we used last time, talking about exothermic or endothermic processes. So exothermic, remember, means heat is released, and endothermic means heat is absorbed. So is boiling an exothermic or an endothermic process? Boiling is endothermic because you have to put energy in to get it to boil. You see that? So then the opposite, what's the opposite of boiling called? When you go from a gaseous water to a liquid? Condensation, right. Yeah, so condensation, is that endothermic or exothermic? Exothermic. So that releases energy. So what do you think is, and this is a question in your lab, what do you think is worse? Getting a burn from boiling water or getting a burn from steam?
Steam.
The steam is worse. Why is the steam worse? You just know it is?
Yeah.
It's not hotter, actually. I mean, it might be a little bit, but let's assume the steam and the water were both at 100 degrees. That steam would still burn you way worse.
Isn't it like, I feel like a steam burn is always bigger too. Like it's deeper and bigger.
It could be, but why? What's so bad about steam? Yeah. Right, exactly. So all that 540 calories per gram, we're saying that condensation is exothermic. So when steam condenses on your skin, all that extra energy goes into your skin. When hot water goes in your skin, it just cools down. So it's still like giving energy to your skin as it cools, but not nearly as much, right? 100 calories, even, let's see, what's body temperature? Like 37, right? So if water cools from 100 to 37, that's 63 degrees, right? So 1 gram of boiling water hitting your skin would give off 63 calories of energy into your skin. But a gram of boiling water hitting your skin would give off 540 calories and then also the 63 calories. So that's why it's so much worse. It's giving off so much more energy that way. We can say the same kind of thing in the other side, talking about melting. We can say that melting ice absorbs energy from its surroundings to melt, right? And freezing ice gives off energy. So has anybody ever done the ice cream trick with this, making ice cream with like actual ice? You done that? What do you put in with the ice?
So,
Salt. Has anybody else ever done that? You don't know what we're talking about. Yeah, you put salt in with the ice, and you put it on the outside of the container with your ice cream in it. Why? You know why you would do that? So if you want to make ice cream, well, okay, we need to talk about the theory of ice cream making first, I guess, for this to make sense. What makes ice cream so delicious? I mean, there's lots of reasons. The flavors, the sugar. But what makes ice cream special? Like, what's special about ice cream? It's not true in other frozen things. No ice cream experts here. The thing that's special about ice cream is the ice crystals are super, super small. So if you just make up like some milk and cream and sugar and you put it in the freezer, what happens? Nobody's done this. I guess I should just tell you, nobody knows anything about ice cream. If you make up like an ice cream batter and you just put it in the freezer, it's just going to turn into a solid brick of ice. It's not going to be ice cream. If you let ice cream melt and then you put it back in the freezer, it just turns into a solid brick of ice. It's not delicious ice cream. The special thing about ice cream is that the ice crystals are so tiny that they don't organize into this big ice block. They get this kind of creamy texture. So in order to get ice crystals to form super tiny, you have to do two things. You have to mix it constantly while it's freezing, so that the ice crystals don't have the time, or the ice crystals can't like organize themselves because they're constantly being churned up. And then you also have to freeze it as fast as you can, because the faster you freeze it, the less time you give the water molecules to align themselves and make ice crystals. So that's how you make tiny crystals. So you agitate, you agitate, you agitate, and then if you're doing it by hand without a machine, you put a bunch of ice on the outside with salt in it. If you just use plain ice, it's not going to work, but you use a bunch of salt instead. And what does that do? It has to do with this, something like this. What happens if you put salt and ice? It does, but like in this winter, let's say, there's ice on the roads, they put salt on it, what happens? It melts, right? The salt forces the ice to melt. And not by heating it up or anything, but by kind of interfering with the crystal structure of the ice. So the salt forces the ice to melt. And if you force the ice to melt, that means you have to take that 80 calories per gram from somewhere to make it melt. And so what happens in the ice cream is it's pulling energy out of the ice cream and makes the ice cream super cold. Cools it really, really fast because you're actually getting way below zero when you put that salt in it, 0 degrees C. You can get below the melting point of a substance because you're sucking that extra energy in by forcing it to melt. So those are some ways that we can play with this. So in lab today, we're going to do all of these things. We're going to melt ice. We're going to boil water. Sounds like an exciting lab, doesn't it? But we're going to measure them also, so that makes it more fun. And we're going to observe some chemical reactions that deal with heat exothermic versus endothermic. All right, so one last question. Why are the slopes of the angled lines different? You could see the ice, to heat up the ice is a pretty steep line. To heat up the water kind of gets a little shallower. And then to heat up the gas gets a little steeper again. Why is that? What is that showing? Yeah.
It takes longer for the ice to absorb the heat as it's turning. Well, it's a short amount of time for the ice to absorb the heat as it goes from the solid to melting. Right.
Well, yes, but let's use a different language of heat instead of time. You're right. If we were adding heat at a constant rate, it would be faster. So yes, this one's steeper, which means that it takes less heat to go that much temperature. And what does that tell us about specific heat of those different substances? Right, the liquid is, right?
The specific heat of the
Yes.
ice would be lower than the water.
Yes, right. Right, so the water having a shallower slope means it's harder to heat it up. So it's a higher specific heat. And then the ice is easier to heat up, so has lower specific heat. And if we go back up to the table, you can see that right here. Liquid water has that specific heat we've been talking about. Solid water has less than half the specific heat. So it takes less energy, it takes half the energy to heat ice up the same distance as it does to heat water up, because it just heats up faster. So. All right, so let's go do it. We'll go do some lab, and it should be fun.